Welcome back, everyone, to another deep dive.
Oh, yeah.
So today,
Today's a fun one.
we are really putting on our thinking caps
Thinking caps, for sure.
because we're going deep into the quantum world,
Absolutely.
talking about two concepts that really kind of mess with how you see reality.
Yeah, totally.
Superposition and entanglement.
Big words.
They are big words, and they're even bigger ideas.
Huge.
And we have a great essay to guide us through this.
Yeah, I was really impressed with this essay by
By Yergo Schnipp.
Dergosh-Nephat. Yeah.
So before we get into the really complicated stuff,
Yeah.
can you kind of give us like the elevator pitch
Sure.
for superposition and entanglement?
Yeah. So, I mean, superposition is, think of it this way. It's like, when you flip a coin and
Yeah.
it's spinning in the air,
Uh-huh.
it's both heads and tails at the same time
Right.
until it lands.
Until it lands.
That's kind of the idea behind superposition, at least an analogy for it, that a particle can be in multiple states at the same time until we measure it.
And entanglement is even weirder.
Even weirder.
It's like two particles, no matter how far apart they are across
Yeah.
the universe,
Yeah.
they're linked.
Linked.
So if you know the state of one,
Uh-huh.
you instantly know the state of the other one.
It's like they're communicating faster than the speed of light,
Right. Which is
impossible according to,
according to everything we know about physics.
Right.
So let's take a step back.
Sure.
Snepot starts off his essay by kind of reminding us how we even got to quantum mechanics.
Yeah.
Like, what was the problem?
Well, the problem was that classical physics, which is what, we use to describe everyday life, works great for throwing a baseball or predicting the motion of planets.
Right.
But when scientists started to study things at the atomic and subatomic level,
Yeah.
they ran into some phenomena that they just couldn't explain with classical physics.
So classical physics was failing
Failing, yeah.
at the really small level.
Exactly.
So what were some of these things?
Like one classic example is black body radiation.
Okay.
So, any object, when it's heated, emits light, right?
Oh.
Like think of a hot stove burner glowing red.
Yeah.
Classical physics predicted that the hotter an object got, the more energy it would radiate at all frequencies of light.
Okay.
But when they actually measured this,
Yeah.
it didn't match up.
So the experiments weren't matching.
Not at all.
Sure.
At high frequencies, especially ultraviolet and beyond, classical physics predicted that objects should emit an infinite amount of energy, which obviously isn't happening.
Yeah.
So they called it the ultraviolet catastrophe.
That sounds bad.
Yeah, it was a big problem.
And this is where Max Planck comes in.
Planck, yeah, he comes in with this radical idea in 1900.
Yep.
He says that energy, instead of being a continuous flow,
Wow.
actually comes in these discrete packets.
So it's not this smooth flow. It's like steps.
It's like steps or chunks, yeah.
Okay.
And he called these packets quanta.
Quanta. So it's like a staircase
Exactly.
instead of a ramp.
Yeah, that's a good way to think about it.
So energy isn't this smooth, continuous thing. It's like quantized.
Quantized, exactly.
And that was a pretty big deal.
Yeah, it was huge.
It was a paradigm shift in physics.
Absolutely.
It laid the foundation for the entire field of quantum mechanics.
Because it introduced this idea that at the very smallest level, things aren't as continuous and predictable as we thought.
Right. So classical physics,
Mm-hmm.
If you know the starting conditions,
Mm-hmm.
you can predict the future.
Deterministic.
Quantum mechanics.
It's all about probabilities.
probabilities.
We can't say for sure what a particle will do,
Yeah.
only what the chances are of it doing certain things.
Yeah, and that leads to one of the most, I think, famous and mind-bending principles of quantum mechanics,
Yeah.
Heisenberg's uncertainty principle.
Right. So this is what Schneppat explains as the idea that we can't precisely know both a particle's position and its momentum at the same time.
Okay, so it's like if you know where it is,
Uh-huh.
you don't know where it's going.
Exactly.
And if you know where it's going,
You don't know where it is.
you don't know where it is.
Right.
So there's this fundamental limit
Yeah.
to how much we can know about a particle.
It's not that we just don't have good enough instruments.
Right.
It's built into the fabric of reality.
It's a fundamental fuzziness to the universe.
Exactly.
At that level.
Yeah, and this fuzziness, this uncertainty, it's kind of a key theme in quantum mechanics.
And then Schneppat goes on to talk about something that always kind of blows my mind.
Yeah.
This idea of wave-particle duality.
Right. It's this idea that, things that we think of as waves, like light, can also behave like particles.
Right.
And things that we think of as particles, like electrons,
Yeah,
can also behave like waves.
So things can be both a wave and a particle.
Yeah, it's weird, right?
Like,
Like,
at the same time.
it's one of those things that just doesn't make sense in our everyday experience.
It does not compute.
But the experiments show that it's true.
So what kind of experiments are we talking about?
Well, one of the most famous is the double slit experiment,
All right.
which Schneppat describes in his essay. And it's basically you shine a beam of light
Okay.
at a barrier with two slits in it,
Yeah.
and you look at the pattern that forms on a screen behind the barrier.
Right.
Now, if light were just a wave,
Mm-hmm.
you'd expect to see, two bright spots on the screen.
Corresponding to the two slits.
Right, that's not what happens.
What happens?
You get this pattern of bright and dark bands,
Okay.
an interference pattern.
And this is like what you would see
If waves were going through both slits and interfering with each other.
So even though we're sending light, or even individual particles like electrons, one at a time, they're somehow acting like waves and going through both slits at once.
Yeah. It's like each particle is spread out like a wave.
And it's in multiple places at the same time.
Which brings us to...
Superposition.
Exactly.
All right, I am hooked.
Ooh.
Tell me more about this superposition.
Okay, so...
It's this idea of being in multiple states at the same time.
Yeah.
It's a lot to unpack.
It is. Superposition is like one of the core principles of quantum mechanics. Schneppat really emphasizes that. It's the idea that a particle, like an electron or a photon, can exist in multiple states at the same time. Until we measure it, that is.
Okay, so it's not just that we don't know what state it's in.
Right.
It's that it's actually in all those states simultaneously.
It's both and neither until
Oh.
we make a measurement. It's like, imagine spinning a coin in the air again.
Okay, I like that analogy.
It's heads, it's tails, it's both until it lands, and then boom, it's one or the other.
So measurement forces it to choose a state.
Kinda, yeah. It's more like the act of measuring forces the superposition to collapse into a single state.
Mm-hmm.
And this is where, our everyday intuition just breaks down. It's hard to wrap our heads around something existing in multiple states at once.
It definitely defies common sense. And I think Schneppat uses a very famous thought experiment to illustrate this, right?
Yeah, Schrodinger's cat.
Ah, yes. The cat in the box. Always a crowd pleaser. But seriously, can you walk us through that again?
Sure. So picture this. You've got a cat, an unfortunate cat stuck in a box.
Poor cutie.
And in this box, there's also a device with a radioactive atom, which has a 50-50 chance of decaying within, say, an hour.
Okay, so a ticking time bomb, essentially.
In a way, yeah. And if the atom decays, it triggers a mechanism that, well, it's not pretty for the cat.
Right, let's not get into the gory details.
The point is, until we open the box, we don't know if the atom has decayed or not.
So it's in that superposition of states.
Yeah.
Both decayed and not decayed.
Right. And here's the kicker. Because the cat's fate is tied to the atom, the cat is also considered to be in a superposition.
Wait, so the cat is both alive and dead?
Until we open the box and look. At that moment, the superposition collapses, and we see either a very relieved cat or, well, not.
Okay, that's heavy stuff. So this thought experiment, it's not about actually torturing cats, right?
No cats were harmed in the making of this thought experiment. The point is to show how this concept of superposition, which seems so weird at the quantum level, could theoretically apply to larger objects too.
So even a cat could be in multiple states until we measure it.
It highlights the strangeness of quantum mechanics for sure. But, in reality, isolating a cat like that is impossible.
Right, too many variables.
Exactly. Too many interactions with the environment. But it gets us thinking about the implications of superposition.
Speaking of implications, are there any real-world examples of superposition beyond these thought experiments?
Oh, tons. Superposition is actually the basis for a lot of technology we use today. For example, think about electrons in an atom.
Okay.
They don't orbit the nucleus like planets around the sun. Instead, they exist in this cloud of probability occupying multiple energy levels at the same time.
So they're in multiple places at once.
It's more like they're smeared out across different energy levels until we measure them. And this is crucial for understanding how atoms bond to form molecules and ultimately how everything we see around us is built.
So superposition isn't just a theoretical curiosity. It's actually shaping the world around us.
Big time. And maybe the most exciting application is in quantum computing. Schneppat touches on this in the essay.
Yeah, I remember that. Quantum computers are still kind of in their early stages, but
they have the potential to be incredibly powerful. And it all comes down to qubits, which are like the quantum version of bits in a classical computer.
okay, so how are they different?
Well, a classical bit can be either 0 or 1, but a qubit thanks to superposition, can be 0, 1, or both at the same time.
Like both at the same time.
It's mind-blowing, but yeah. And this allows quantum computers to explore many possibilities simultaneously, giving them a huge advantage over classical computers for certain types of problems.
So we're building computers based on the very principles that make our heads spin.
It's a wild time to be alive. But, before we dive too deep into the quantum computing rabbit hole, let's go back to Schneppat's essay and talk about the other big concept, entanglement.
Oh yeah, entanglement. That's the one where two particles are linked across potentially vast distances.
Exactly. And it's one of the most baffling aspects of quantum mechanics. It's like they're connected by an invisible thread, even if they're light years apart.
So if I measure the state of one particle here on Earth,
The state of its entangled partner, let's say on a distant star, is instantly determined.
like faster than the speed of light.
It seems that way, which is why Einstein called it spooky action at a distance. It really challenged his ideas about relativity.
Yeah, I bet. I mean, nothing can travel faster than light, right? That's like physics 101.
And that's why even Einstein had trouble with this concept. He, along with Podolsky and Rosen, came up with this thought experiment, the EPR paradox, to try and explain it away.
What was their idea?
They basically argued that quantum mechanics must be incomplete, that there must be some hidden variables, some underlying mechanism that we haven't discovered yet that could explain this spooky action without violating relativity.
So they thought there must be some sort of like secret communication going on.
Something like that. But then along comes John Bell in the 1960s, and he throws a wrench into everything with his famous theorem.
Ah, yes, Bell's theorem. Schnepp definitely went into that. But to be honest, the math got a bit dense for me. Can you break it down in a way that even I can understand?
Okay, so Bell's theorem essentially provided a way to experimentally test whether Einstein's idea of hidden variables was correct. Bell came up with these inequalities that would hold true if hidden variables existed.
So like a mathematical test.
Exactly. And the amazing thing is, experiments showed that these inequalities were violated, meaning that Einstein's idea of hidden variables was wrong. Quantum mechanics really is as weird as it seems. There's no secret communication, no hidden variables. Entanglement is just, well, entangled.
So Einstein was wrong about this. That's kind of mind-blowing in itself.
It shows that even the greatest minds can be challenged by the strangeness of the quantum world. And this spooky action at a distance, it's not just a theoretical curiosity. It has the potential to revolutionize a lot of things.
Like what?
Well, one of the most exciting areas is quantum communication. The idea of using entanglement to send messages that are completely unhackable.
Unhackable. Sign me up. How does that even work?
Okay, imagine you have two people, Alice and Bob, who want to communicate securely. They each get one particle from an entangled pair.
So they're linked, even if they're far apart.
Right. And because of that link, any change Alice makes to her particle will instantly affect Bob's particle, no matter the distance.
So it's like they have this secret code that no one else can decipher.
Exactly. Any attempt to eavesdrop or intercept the message would disrupt the entanglement. Alice and Bob would immediately know that something's up.
So quantum mechanics is giving us the ultimate in cybersecurity.
It's one of the most promising applications. And this is just the tip of the iceberg. Quantum computing, quantum cryptography. There's so much potential in this field.
It's amazing how these ideas, which once seemed so abstract and theoretical, are now finding practical applications. It's like science fiction becoming reality.
It is. And all this talk about superposition, entanglement, quantum computers, it makes you wonder about the bigger picture. Does quantum mechanics change how we view reality itself?
I mean, yeah, it definitely makes you think, like,
Yeah.
if particles can be in multiple states at once,
Mm-hmm.
and they can be linked across the universe,
Yeah.
what does that even mean about reality?
Right.
Like, what is real anymore?
I mean, that's a question that philosophers have been grappling with, since the dawn of quantum mechanics. I mean, Schnepp gets into this too.
Right. Like, one of the biggest questions it raises is, does an objective reality even exist?
So, is the world out there even when we're not looking at it?
Exactly. Or does the act of observation, does measurement actually create reality?
Oh, man.
It's a mind-blowing idea.
I know.
And if we go back to Schrodinger's cat,
Yeah.
does the cat experience being both alive and dead?
Or do we, by opening the box, decide its fate?
Right. It's like, do we play a role in creating reality just by observing it?
Yeah.
And this is where, different interpretations of quantum mechanics come into play.
Okay.
There's no one agreed upon answer.
Right.
But one of the The most popular is the Copenhagen interpretation.
Okay, I've heard of that one.
Yeah, and it basically says that, until a measurement is made, a quantum system exists in this superposition of states.
Yeah.
And the act of measurement causes it to collapse into one definite state.
So there's no objective reality.
At least not according to the Copenhagen interpretation.
Until we measure it.
So we're creating reality.
In a sense, yeah.
Wow.
It's a pretty radical idea.
I mean, that's a lot of responsibility.
It is.
But then there's the many worlds interpretation.
Right.
Which is even weirder.
Yeah.
That's the one where, like, every time a measurement is made, the universe splits.
It splits.
And there's a new universe for every possible outcome.
It's every possible outcome, yeah.
So, like, there's a universe where Schrodinger's cat is alive.
Uh-huh.
And another one where it's dead.
Exactly.
And we're just in one of those branches.
Yeah, it's like instead of the wave function collapsing, it just keeps branching out.
So there are infinite universes.
Potentially, yeah.
With infinite possibilities.
It's a mind-boggling concept.
It really is.
And, there's no experimental evidence to prove or disprove it.
Right.
But it's a fascinating way to think about the implications of quantum mechanics.
So every choice we make creates a new universe.
Potentially.
So there's like a me out there who decided to wear a different shirt today.
Maybe.
And another me who, I don't know, skipped breakfast.
It's kind of a dizzying thought.
Yeah, I mean, it makes you wonder about free will, right? If all these possibilities are playing out,
yeah,
are we really making choices?
It's a deep philosophical question.
Or are we just like along for the ride?
And an entanglement.
Yeah.
It adds another layer to this whole philosophical puzzle.
How so?
Well, I mean, if these particles are really linked instantaneously across vast distances.
Yeah.
Does that imply some kind of faster-than-light communication?
Which we thought was impossible.
Right.
Or does it mean that our understanding of space and time is just like completely wrong?
Yeah, it challenges some of our most fundamental assumptions about the universe.
Yeah, I mean, it's amazing how these concepts that started out with trying to understand light and atoms lead us to these really deep philosophical questions.
Yeah, I mean, it's a testament to the power of science, right? To not only, expand our knowledge of the physical world,
But also
but also to make us question
Yeah.
our most basic assumptions about reality.
and ourselves.
Exactly.
Well, this has been a truly mind-bending deep dive.
It has.
And I really have to thank Jorgo Schneppat for his essay.
Yeah, Schneppat's essay was a great guide for us.
It really helped us navigate these complex and fascinating ideas.
He really captured the sense of wonder
Yeah.
that makes quantum mechanics so intriguing.
To our listeners, if you're not already fascinated by quantum mechanics,
Yeah,
we hope you are now.
I hope so.
It's a world of mystery and wonder.
Yeah.
And it's a world that's constantly challenging us
To rethink everything we thought we knew
about the universe
about the universe.
and about ourselves.
Absolutely.
So keep questioning, keep exploring, and who knows what other mind-blowing discoveries await.
That's the fun part.
Yeah, that's the beauty of science.
It's always evolving, always pushing the boundaries.
And that's it for this deep dive.
Until next time.
We'll see you next time.